Welcome back everyone, and in this and also likely in the next video we want to not specifically talk about something that is related to a certain method. We more want to talk about what I would say belongs to like the good practice of data analysis. And there are many things that you need to consider when you work with real data. So I'm trying to give you a kind of a comprehensive overview, but definitely this is not going to be a complete overview of all the possibilities that may occur during real data analysis, but we will go to some things that you should always have in mind when you start analyzing your data. So the first thing is usually when we have data, our data is collected, in our case likely by someone else, but what will occur usually is that for some variables there may some realizations be missing. Okay, so the reason is whatever, but it will be the case that you observe a data set that for certain variables in certain rows there will be a no value, and a missing value is typically indicated by an NA, so not available, or an NaN, a not available number, or something like this. And there are different strategies that can be followed when it comes to the handling of missing values. So what I would recommend is, first of all, usually we work with a pandas data frame. And the pandas data frame, as you have already seen in other videos, provides the info method, and the info method already shows you how many is null. So is null is if there is a null value, and a null value is a missing value typically. So it shows you per variable how many missing values there are in the data set. So, and if you identify that there is a variable which mainly has missing values, then what I would recommend is to completely delete this variable, because I would say if there are so many missing values, then this variable is not likely to be reliable, and we should not rely on it if we create our model. If there are only a few missing values, and if what you consider to be a few and the majority of missing values, obviously something which is subjective, but yeah, that's just the way it is. But if there are only a few missing values, then you may want to use what's called data imputation techniques. And also here there are different possibilities how you can impute the data. What's meant by it is that you replace a missing value by a value which would you consider to be a good representative value for the value that is missing. And there are like easy ways that we can follow here, and there are more advanced ways. Luckily for us, this is very well documented in the sklearn package, and also it is quite easy for us to do this using the methods provided by the sklearn package. So let's just quickly go there. If you Google data imputation and sklearn, you are likely to end up at this page here which says imputation of missing values. I would highly recommend that you read this on your own. But as you can see, it starts by discussing that there is the possibility of so-called univariate imputation and multivariate imputation. Univariate means that we only use the information of the specific variable for which we are going to create the missing values. And multivariate imputation means we're also using the relationships among all variables in order to find good representative values for a specific variable with missing values. As we are beginners at the moment, I would recommend more to use the univariate imputation techniques, and they are kind of intuitive, and also something that you probably would do on your own without watching this video. So you can find some easy examples here in the 99 additional code file in your Google Colab folder. And here we can see how it works. For instance, if we have a single numerical variable with, in our case, a single missing value, and if you have a numerical variable, then it typically makes sense to replace the missing value by either the arithmetic mean of the variables of the values that are available, or by the median. The median is preferable, especially if the distribution of the realizations that we can observe here is quite skewed, then I would recommend to use the median. Otherwise, it's also completely okay to use the average of the values that are available in order to replace this missing value with this average and consider to be a good representative value for the variable itself. sklearn, as you will realize, always does things in very similar ways. So here we have the simple imputer class, and here then we create an object of this class, and within it we can define certain things. So in our data set here, the missing value is specified by the numpy nan. It could be, for instance, in your data set also by something else, maybe by a string which says NA or whatever. This is something you may need to identify first, but then you can define what are the missing values in your data set or for your variable. And here you can say strategy mean to use the average of the available values. You could also use the median here. In this example, it would lead to identical values, but once we have a skewed distribution here, the values will differ. And then you need to fit it, and fit just evaluates the average of the available values here. And then you can use the transform method in order to really replace the missing value by its representative value. And what is happening then is you can observe it here. So here we have the original data with a missing value, and this missing value is replaced by the average of 1 plus 2 plus 4 plus 5. And yeah, I think quite intuitive here. The next thing, if you have categorical data, for instance, as it usually is in raw data format given by a string realizations, then obviously this is non-numerical and it doesn't make sense to look for an average value here. But what's most common here is then to use the most frequent realizations of the categories in order to use this one as a representative for the missing value. And yeah, this is like how it works, and it's more or less exactly the same, except that you really need to define a certain strategy here which matches the original nature of the variable. Okay. Then what's also available in the sklearn package would be the multivariate imputation. You can read about it here. I think it's very well described. So without going too much into detail here, typically we will have different variables, especially different feature variables, and there might be some relationships between the feature variables and its realizations. So when we use multivariate feature imputation, what we do is we, in an iterative manner, for instance, if we want to replace the missing values of the second feature variable, then we use the first, the third, the fourth, and whatever number we have of feature variables in order to create a forecasting model for the second feature variable. And then we use the forecasts, knowing the information of the remaining feature variables, in order to make a prediction for the missing value. May sound complex at the moment, is less complex than you think, and you can do this for all the feature variables with missing values in your data set. And this is circling around in an iterative manner here when you use the sklearn implementation. But as I said, let's not go too much into detail here at the moment. I would recommend to stick with the the easiest possibilities of missing value imputation, and that is given by the univariate imputation methods here. So this is the first thing you may want to look at when you have a data set. Then what's also has to be done, usually for most of the models we are using, and it never, in my experience, even though it's not mandatory or it doesn't really need to be done for the model of your choice, it still can be valuable if you still do it. And this is pre-processing all the variables, and usually pre-processing in the sense that we want to scale the variables. We want to bring them, each feature variable, to the same comparable numerical range. Usually this comes along with numerical stability when it comes to the estimation process of the models, and it also makes the the comparison regarding the feature impact possible, because if all the feature variables have their values in a similar numerical range, then the effect size that we are going to estimate, usually represented, for instance, by the parameters, especially if we stick to more easy models like the linear regression or logistic regression model, then having the feature variables on similar numerical ranges makes the effect sizes directly comparable. And for more complex models, for instance, for neural networks, which we are going to discuss at the later stage during the semester, it is kind of necessary to bring the feature variables to the similar numerical ranges in order to really have the numerical stability which we need for estimating the models. There are different ways when we want to bring the feature variables to similar numerical ranges. I would say the most common ones are standardization and standardization, or like the min-max standardization, and this is what we consider maybe like a standard normalization. So basically what we do here is that we have in the original state for a specific feature variable some values which are, I don't know, in a certain numerical range, let's say for instance between -100 and 100, and when we use the standard normalization method, we derive the arithmetic mean for the specific variable and its empirical standard deviation, and then we use each value. From each realization that we have for the feature variable, we subtract the mean and we divide by the empirical standard deviation, and this will lead to a new standardized version of this feature variable, which has now a mean of, or an average value of 0 and a variance or a standard deviation of 1. The min-max standardization is different and has a different impact regarding on the range where we bring our transformed version of the feature variable. But what we do here is we derive the minimum value and the maximum value of all the realizations that are available for a specific feature variable. And then we process each realization in the way that's defined here. So that means we subtract the minimum value of all the realizations that are available, and then we normalize this by dividing through the span between the maximum and the minimum value of all the realizations for a specific feature variable. And this leads to a standardized version whose values are now all in the range between 0 and 1. This could be, for instance, also adjusted or altered in a way that we could have the values between -1 and 1. Furthermore, especially if we have feature variables with many outliers or some things, then we could also use more or different techniques here of standardization, for instance, like a quantile transformation and so on and so on. Again, there are many possibilities here. They are all very well documented with the sklearn package. So if you're interested, you could simply search for pre-processing data. And then here again, you will also find good explanations of the things we are doing here. And you also will find different explanations for more advanced methods, or for not advanced, but for alternatives. So such things as a robust scaling, which is given here, or let me see, then we have a kernel center scalar method, and here the quantile transformation. So a lot of information for you, and you should rather consider this to be a beginning. And in the beginning, we may just use the standard normalization or the min-max standardization techniques. But just keep in mind that especially if we have feature variables with many outliers, this can cause problems, and then we may need to, or we may take into account different standardization techniques. The techniques I've explained so far, they are only well suited if we have real valued feature variables. If we have a feature variable which comes into categories, Usually in the raw format, the categories are given by some string values. So for instance, red, blue, green, and whatever. And then there are two things that you can do. You can do the ordinal encoding, which is given here. Ordinal, as the name suggests, is only reasonable if there is a ordinal variable behind the categorical feature. So for instance, it could be good, neutral, and bad. Then there is some rating for the category feature, and it may make sense to take into account this ordinal structure and then use the ordinal encoder. Otherwise, it is very common to use what is called one-hot encoding. And yeah, let's just go over to our short examples here. So, then I will explain in more detail what one-hot encoding is. So first of all, here in the beginning, you can see the standard scalar and the min-max scalar. And as you will see, it's always the same how we can use it with sklearn. So here is our raw data from the beginning. Then in the first step, we would have replaced the missing value by the value of 3 here. And then if you want to now scale the data or this feature variable, then for instance, we could use and define an object of the standard scalar class. And then we directly can use the fit transform method. It does two things in one step. First of all, it fits the data. Fitting means here, if you use the standard scalar, it derives the arithmetic mean and the empirical standard deviation, which is needed in order to transform the realizations. And then in the next step, it does the transformation as it is defined also in the slides that we previously visited. And as you can see, the impact, or you can see here how this works out. So in the beginning, we have data with missing value, then we have the raw data, and then we have data which is somewhere centered around the average value here. For instance, if you want to, and I would highly recommend you can play around with this. You may, for instance, for a second, replace the standard scalar by the min-max scalar. And now you can see that the data is now in the range between 0 and 1. If I recall it right, let me just take a look. You can, when you use the min-max scalar, then you could also define the range in which you want to have the values. So here you have the feature range, which by default is between 0 and 1. So for instance, if you want to have our values between -1 and 1, this is also possible, and you simply need to define it here, and then you can see how it is done here, okay? So let's go back to the standard scalar and delete this. And if you're interested, you also can see here, for instance, how the min-max scalar works and is defined here, okay? And all these methods, they all come along with an inverse transform. That means once you have the scaled data, then you can use the scaled data and use the inverse transform method on it, and then you will have the raw data again. You will see how this works during our course when we watch many examples where we want to, in the end, get the original and raw versions, for instance, of a target variable that we also may have previously scaled to a certain range before we train the model. Last but not least, here, the ordinal encoder, you can see how that works. What's important to know for you is that it automatically derives the values for the corresponding categories, and usually it does that by an alphabetical order. So that is what we have for good. We have a value of 0 here. For neutral, we have a value of 1 here, and for worse, we have a value of 2. If I would replace worse with bad, then bad gets the value of 0. Yeah, as you can see here. Good, the value of 1, and neutral of 2. So yeah, you need to really make sure that this works out as you need it, and you can find in the documentation of the ordinal encoder how you can specify the ordering on for yourself. But yeah, let's not do this here, because I think this is something you that you will not need that many times. Now, one-hot encoding is something which I would say is what you will use more often. So typically, it's what you do here when you have a variable with 3 categories. So let's add some values here. Assume we have more realizations, but still with 3 categories. Then if we have 3 categories, then each realization will now be represented by a vector of with a dimension of 3. So the vector will have 3 values. It will have zeros except for the category it represents. Okay, here, so for instance, if we have in the raw version, if we have the realization neutral, neutral is now going to be represented by a vector of the length 3 with a 1 at the second position. Good, for instance, is now represented by a vector with zeros except for the first position where we have 1. So that's why it's called one-hot encoding. And yeah, as you may realize, it also seems to, so the position at where the 1 is given also depends on the alphabetical order of the original categories here. Okay, good. So I hope this makes it more clear. And now this is like at this point when we have like pre-processed the data. So we have the raw data, we have checked it for missing values, we may have replaced missing values, we may have brought all the feature errors either to similar numerical ranges or may have one-hot or ordinal encoded them. Then usually we are good to go in order to start our model estimation process. And this is then going to be done with splitting the data in certain ways. And this is what we are going to take a look at in the next video. So check out the next video and see you there. Bye-bye.